finally we've got a system of equations, AU is equal to B, and we have solved it, right. So now the usual problem is find out the far field, right. So again, just to give a schematic over here, this was my, let's say, my aircraft, okay, and let's say this was my computational domain. Right, and I want to find out and this is being illuminated by some, let's say, a radar field over here, and I am standing over here and I want to find out what is the field over here. Okay. So computing the far field, is there, what kind of strategy do you think we'll have to do? Should I expand my computational domain to go all the way to the receiver? Is that necessary? No. So what should I do instead? Incident wave is some wave, it's given to you. Now I want to find out the far field. What have I found out so far? So let's say I solved my AU is equal to B. This is my computational domain. So there are, triangles everywhere and so on. So what have I got at the end of this calculation? What have I got? U's. So I know the field everywhere inside the domain. But now I want to find out the field somewhere far away. What do I do? So that's what one thing that is being suggested is that, well, if you want the field somewhere far away, somehow I have to expand this domain to include this fellow. That is what is called a brute force way of doing it. Is there a smarter way of doing it? Brute force way is one way. Supposing I want to find out the radar cross section, that means my observer is where? Infinity. Can I possibly mesh so much? So what was the very start of this course? We talked about Huygens principle. So what does Huygens principle tell you? If I know the tangential fields on a closed contour, they act like secondary sources and I can propagate them and find out the field everywhere. So how will I apply this principle here? Do I know the fields on a closed contour enclosing the object? I do. So I mean, for example, this boundary itself is a closed boundary enclosing the object. Okay. So I can use this boundary. I know I have calculated the fields over there. I can use that to apply Huygens principle and find out the field anywhere. That is one thing. Now we have had a discussion on boundary conditions, and we have seen that for example, the radiation boundary condition we have used, it's inexact. So the error of the boundary condition grows as I get closer and closer to the boundary. As I move further inside, it gets better. I am just giving you information, we have not actually calculated it. So what would be better is that if you in your mesh itself you had a nice set of edges like this, which defined a boundary. Okay. So when you use your CAD software, you sort of define let's say a circle or something around it, and what the meshing software will do is it will respect that edge. So it will align the triangles to be in such a way that you get one nice smooth set of edges. So there will be U1, U15, U25, whatever. Those are the U's that are sitting over here on this contour. So you now know the field on those points. Okay. So brute force is a bad idea. Instead, we will do Huygens principle. Okay. So for example, this is an expression which we have calculated several times. The field at any r as per Huygens principle. So ES is scattered, that is what I want. What is that an integral? It is a contour integral over, let us call this a contour r. Okay. What are the terms that will come here? So this is scattered only. So it's the E total is phi incident plus phi scattered. So remove the phi incident. So I am only calculating the scattered field. So the first term, so remember this is going to be G and grad G, those are the two terms, right? So the first one will be Ez at r prime, grad G of r prime minus, so let me put in the dot n hat over here, minus right, and dl, let's call it dl prime because I am going over, this is my contour, right. We are still in the TM polarization, that is why I have written this as Ez. Okay. Do I know Green's function? That is the question. Yeah, so in this case, once since I have taken the contour to be, if you go back and recall the discussion of Green's function, I divided space into two volumes, V1 and V2. In Huygens principle, for finding out the field in the outside region, which Green's function do I need? Of the outside region or the inside region? The outside region. In this case, what is the outside region? Free space. So I know this G. It's simply my Hankel H02 or whatever, right? So the good part is I know the Hankel's function. Further, what else can I say? I can make all the standard approximations that I had done for your Hankel function, which is what? That H0 to k rho, right? So for rho much greater than 1, we had approximated this as 2j by pi k rho e to the minus j k rho. So all of these approximations we can substitute inside over here. Okay. In this, so finally before we end this discussion, in this expression, do we know everything? Have we calculated everything? Let us go step by step. Ez at r prime, or let us start from the right hand side, let us make it simpler. Remember, this is 2D TM polarization, which means H in xy plane and E z. These are the two variables, three variables. Do I know this term? Yes, we had shown that this is proportional to H tangential. Have I calculated H tangential? That was exactly my variable in the problem. They were the tangential edges, right? So that's another nice part about the edge based FEM that I got straight away this thing. So I know this. What about this guy? Do I know this guy? I don't know it, but can I calculate it? How? Maxwell's equations means taking curl of H will give me E. How do I take curl of H now? I know H as numbers, I don't know it as numerically, right? So now I know everything inside this. So numerically I have to take the numerical curl of H. That is why it is important for my mesh to be very fine, so that the numerical approximation is more or less correct, right. And once I have got this, then my favorite expression is for your RCS. What was it equal to? Limit r tending to infinity 2 pi r Ez scattered, Ez incident do you put r to be a large number? Well, if you, this was part of one of the assignments earlier, if you calculate this expression, this would turn out to be independent of r for r greater than 1 for very large r. So, it does not matter. You do not have to put anything. This expression, the expression for RCS, this expression for RCS will turn out to be independent of r. It will only depend on this theta. Yeah, in the Huygens principle we have g of r comma r prime, but then you have to use these approximations, and when you use these approximations that value of r cancels off. You do not need to substitute anything. If you are substituting it, you are doing something wrong. Yeah, you can take the curl. Yeah, I mean, yeah, that's exactly what we are going to do.
But you said numerically.
Okay, so what I mean by numerical curl over here is, yes, h is in terms of the u's and t's is in terms of x and y, right? I will get some expression for it. Now, if you look at, we are running out of time. This is one edge, this is one triangle, and this is another triangle. If you look at these Whitney basis functions that we have, if you actually go to calculate curl of t, you should do it, you will end up getting a constant because of the form of t. So, what happens is that you get one constant here and another constant here. So, the curl of t is actually not continuous for these basis functions. That is one defect of these basis functions. So, what you will actually have to do is find out the curl here, find out the curl above, and then take an average of it. So, that is what I mean by numerically find out. Yeah, in the end we have a smooth function of h everywhere in the plane. Yeah. But yeah, that is a good point. And another very interesting thing about these basis functions, if you do this, you get 0 for the basis functions we are using. So, we'll work this out in an assignment. Take any one of them. A single basis function has these properties. Curl of t is constant, divergence of t is 0. All right.